Just a bit of an introduction. This is a part of a series of presentations, more than presentations are tutorials that we're working around Python for a community of petroleum engineers and geoscientists. So I was explaining that we have a Slack channel where we have around 800 members in the Slack. People ask questions, and you have a lot of other people share material there and their own repositories. We also have a YouTube channel, which is Oracle Hub, and in there we are recording these sessions and we're uploading all of these sessions. And we have a GitHub where most of the codes that we do are in the GitHub repository. And some of the speakers like Mansoor, they have their own repo in GitHub that they will point out during the session. Mansoor, I think that you can go in. You have more people at least accepted the invite in the Slack.
Okay.
Hopefully they will join us as you progress with your presentation.
Right. Okay. Okay. You guys can hear me? Can you hear me? Okay.
Perfectly well.
Okay. Well, good to know that. Okay. Now I think. Oh. Okay. Let me share my screen then. Okay. Okay. Can you see my screen, please?
Yes.
Okay. Right. So I just wrote this simulator in PVT in Python, mostly to learn Python. That was my objective. And secondly, this, as it were, a secondary benefit of this was that I have previously worked for a company where we did not have a PVT simulator. And at the time, I tried to search for any simulator available online. There wasn't any. So that's why I decided to write this simulator. Okay?
Yes, carry on.
Okay. Right. So I will, what I'm going to do today is just take you through a presentation, which is also available on GitHub. And then I will just take you, we will try one or two compositions and show you how it works and how the results look like. Okay. Right. So let's go through the presentation first. To begin with, I'll just tell you what it is that I'm trying to do. Next, some technical background, very little really. I'm not going to go into equation of state, and some features of the simulator, and then what's the best way to use the simulator. Okay, so once again, let me emphasize that simulator is good to use when you don't have a commercial simulator available for one reason or the other. I know many companies can't afford, or for some reason don't want to have a PVT simulator, or they feel that they don't have enough use for a simulator. So in such circumstances, this might come in handy. And a bit of warning, as it were, the results cannot directly be used in Eclipse. What you would need to do is you might need to do some minor editing. For example, in the PVTO table, it will write the saturated value of RS repeatedly, whereas Eclipse requires that it's only written once. So that is kind of like editing that you need to, which these issues are very easy to fix. I have not spent time trying to fix them. Or there might be some minor editing required with slashes. And for some, I have worked on a few compositions and I've compared them to commercial simulators. They look okay. They don't exactly match, but they look okay. Okay, but for that matter, the two commercial simulators don't match. Right. So Peng-Robinson equation is Eclipse's favorite equation. Eclipse prefers Peng-Robinson 3-parameter equation, and what I've done here is 2-parameter equation, because the third parameter is only is required when you want to correct for densities, etc. So, yeah, for liquid density. So that part I've not yet done. For viscosity, I'm using LBC correlation. And if you go back to original LBC correlation, it uses it, as it were, pseudoizes C7 plus molecular weight, and then uses that as a parameter. I haven't done that. That is half on purpose and half on half because I just didn't feel that it might come later, or that it may or may not have an impact. Okay. So in future versions, I'm also going to include the Pedersen equation. I'm working on that code. Okay. So this can be used. I usually prefer to run it in Jupyter Notebook, but if you can just download it as .py file, as I put it in my GitHub page, you can just run it with the Python command. Okay. So basically, what you need to do is enter the composition of the fluid. And at the moment, I've only made provision up to C16, but that is very easy to extend. If you have properties, critical temperature, critical pressure, eccentricity factor, and molecular weights available for heavier components, you can easily edit this program and add those. So it's not that you got limited to C16. It's just that for my purpose, I've only just put in components up to C16. So it will require composition from you. It will require reservoir temperature, and it will require list of pressures. Okay. So commercial simulators would just ask for the maximum pressure, minimum pressure, and steps. Here, I'm not doing that. I'm just asking you explicitly for pressures on which you want the calculations to be done. And then at the moment, I'm only allowing up to 2 stages in a separator. Okay. And the second stage is usually 14.7 psi and 60 degree Fahrenheit. So if you would also need to identify if the fluid is oil or gas. Theoretically, the simulator should be able to tell on its own, but I was having some trouble there. So I now require you to tell the simulator if your fluid is oil or a gas, which is not hard to know really. So if you tell the simulator if it's an oil, and then it will perform the calculation, it will output solution gas oil ratio, formation volume factor, and viscosity versus pressure. This is the PVTO keyword. And then it will also output formation volume factor and viscosity for gas, the associated gas as it were. And this is PVTO and PVDG keywords. And then you can, if you want to, you can extract the compositions at all stages and definitely at the separator stages. For gas condensates, we require the condensate gas ratio, CGR, or we call it RV, BG, viscosity, and pressure. Okay. And with gas condensates, there is obviously associated condensate. For that purpose, you also need the PVTO property. So it will also do that. And then once again, composition of oil and gas at the separator. So, and then it will make plots for you so that you're going to have a quick check if it's working out right or not. Okay. What I also intend to do is to be able to bring in observed data so that you can make comparison. I should have done that, but I'm just one step behind here. Okay. So for oils, once again, we've already mentioned that it requires composition, pressures, temperatures, the type of fluid, oil or gas, and up to 2 separator stages, and pressure, temperature at each stage. Okay. So this is where you would enter. At the moment, I don't have a graphical user interface. I would like to build one, but once again, that's for the future. But this is, as it were, it's a bit tedious entering composition like this in the form of a dictionary. So here you see that I'm entering the composition here. I'm telling what the reservoir pressure is in degree Fahrenheit and list of pressures. This is where I want the calculation to be done for it to calculate the reservoir fluid properties. So fluid type here I'm specifying is oil. And I'm saying that I've got 2 separator stages. I'm giving the pressure and temperature for the 2 separator stages. Okay, then this is the function, one of the function which when you execute will generate RS, BO versus pressure. Not viscosity, but RS and BO versus pressure. Okay. And then this is another function which just helps us to make plots. Okay. And here I'm using pandas. Okay. So this is what the output might look like. Okay. So pretty much I'm following what Eclipse Simulator does. It's just that if you, I don't know if you can see my mouse, you can see that the RS is increasing, and then it stabilizes. Eclipse doesn't want these values. So Eclipse only wants one saturated value. It doesn't want those values being repeated. So this is where you would have to do some manual work. And you need to be careful about these slashes at the end. Right, everybody with me?
I am.
Okay, all right. Right, so, and it will also output liquid composition, vapor composition at the separator. Now, what I would also like to do is make this, this output a bit neater. At the moment, it's not neat. I would like to make it neater. I think I might just put this in pandas or some sort of Excel sheet, or just play with the number of decimal places. Right, okay. Okay, and the output will also take this form, which is what you would like to look at: solution gas oil ratio, formation volume factor, viscosity of oil versus pressure. And for PVDGS, viscosity of vapor versus pressure, formation volume factor versus pressure. Okay, now let's go to step-by-step guide for gas. When I say gas, I really mean gas condensate, not dry gas, gas condensate. And if you look at it, very similar input, you need to tell, but you must specify that it is a gas, okay? Otherwise it will perform the wrong functions. And you would need reservoir temperature and then the list of pressures, okay? Once again, I'm telling it 2 separator stages, okay? I execute this, this will generate for me RV, BG versus pressure. And there's a different function which you need to execute for viscosity. So this is the function that I used for assimilating them into pandas and then plotting them. And this is how the results would look like. The top table is the PVTO keyword, as it were, for the associated oil, and then PVTG, which is RV versus pressure, BG versus pressure, viscosity versus pressure. Once again, just be careful with the number of slashes, etc. You might need to do minor editing. Okay. This is the viscosity function. Okay, this viscosity function, when you execute it, it generates a table of oil viscosity versus pressure and gas viscosity versus pressure. So if you look at it, look at the results, I am looking at PVTG table, CGR versus pressure, formation volume factor versus pressure, gas viscosity versus pressure, okay. And formation volume factor versus pressure, RS versus pressure, and viscosity of liquid versus pressure. If you're worried that I'm not showing you the undersaturated line, it's generated, but I'm just not showing it over here. It's just showing the saturated line for formation volume factor. Okay, this is future work, of course. This is at the moment I'm using LBC, but Pedersen is a better one to use, but it's a bit repetitive to model. Okay, so I'm working on that. And I want to make separators more modular, to be able to add as many stages as possible and to be able to control how the liquid from stage 1 goes into the next stage, or how the vapor from one stage goes into the next stage. So at the moment, it's simply 2 stages, and first stage liquids goes into the second stage, and the vapor from the 2 stages are basically goes to 14.760 degree Fahrenheit, as it were. So in the long run, of course, I would like to be for it to be able to calculate the first contact miscibility pressure, multiple contact miscibility pressure, and the ternary diagrams, which are very demonstrative in terms of showing the miscibility. Okay, so I will eventually work on those as well. So now, Alejandro, my colleague, gave me Walls data set. Okay, and it's a recombined sample, and this is the composition for the recombined sample. So I ran some tests for it through this my simulator, or I'm calling it Raphael_PVT simulator. I've named it after my son, and a commercial simulator. So let's look at compare the results. So first thing was, the easiest thing that I did was just flash the fluid on this page to 14.7 psi and 232 degree Fahrenheit. Okay, and the commercial simulator gives me 0.08 barrels of liquid. This simulator gives you 0.085 barrels of liquid, which I feel is close enough. Okay, and then if you were to flash them to atmosphere, 14.7 psi and 60 degree Fahrenheit, commercial simulator gives you 0.1937 barrels, and Raphael gives you 0.207 barrels. So to further improve your confidence, I'm also listing the compositions. So if you look at the compositions, the commercial simulator, I'm listing from nitrogen, carbon dioxide, methane, ethane, propane, and then C8, C9, 10. I'm just ignoring because of space. Otherwise, the presentation gets too crowded. So 14.7 psi and 60 degree Fahrenheit, if you flash the wall fluid, you see the compositions are fairly similar: methane, ethane, propane, and the heavier components are definitely very similar. So that should instill confidence in you. Okay. Then once again, I flashed at 14.7 psi, 232 degree Fahrenheit. Similar composition, similar values for methane, similar mole fractions for methane, ethane, propane, C8, C9, and C10. So C8, C9, and C10 are very similar. And then I flashed it wall fluid at 2000 psi and 232 degree Fahrenheit. And I found, once again, the compositions to be very adjacent. So that should establish confidence in the simulator, at least for straightforward flashes. Okay, so this is the end of my presentation. Now I will try and share my Jupyter notebook with you and run through it. Okay. Okay, let me kill this presentation. Okay. Okay, and so can you, Alejandro, can you confirm if you can see my Jupyter notebook?
Yeah, I can see it well. I don't know if you can collapse your left hand side bar, the ones with your bookmarks and all that. I don't know if it's possible, but you can.
Oh, I don't know how to do that.
Just try to click on the book icon again, and probably it will collapse.
Okay.
Oh, Otherwise, leave it as it is. It's just fine.
Okay, it worked. Okay. So this is now I'm showing you the same thing in simulator in Jupyter Notebook. You can see that it was as it were fairly raw, because you can see all my comments and as how I'm going from one version to the other. You're not interested in that, but if you want to trace what I was doing, then this is giving you a little bit of history of how I've been working with. So basically, the important thing is that it's easier if you call the entered composition Z1. It's easier. It's not necessary, but it's just easier. So here I have entered the Wolf dataset that I showed you in one of the last slides. All other compositions that I have previously tested the model on, I've commented them out. Okay. Oh. Excuse me for a second, please. Okay. I'm back. Okay. So I'm providing it with the reservoir temperature and a list of pressures. So they are in ascending order. You need to do that. You need to, at least for the moment, you need to make sure that they're in ascending order. If that is, there's a problem, we can sort it out later. But at the moment, just make sure. I'm specifying the fluid type as oil. Okay. And from what I had gathered from the data set that Alejandro, my colleague, sent me, they had flashed it only directly to atmosphere, 14.7 psi and 60 degrees Fahrenheit. Okay, standard condition, not necessarily atmosphere, but standard conditions. Okay, so I specified one stage, and when I specify one stage, it's going to look at this only. Okay, it's going to ignore this. Okay, so that is just input. Here I am specifying the critical pressures for all components, critical temperatures, eccentricity factors, molecular weights, and critical volume. Okay, this is for viscosity calculation, binary interactions. Okay, so this is just input. May I suggest that if you want to add to it, that's fine, but just be careful, because it's very easy to mess this up. Okay, so I suggest that if you're going to make a copy, and then if you want to add more components, or if you want to play with the molecular weight, temperature, etc., or critical temperature, etc., I suggest that I will show you a way of doing it separately, differently. Okay, so I'm calling this at the moment. Well, if you've downloaded it from GitHub, you might not see this box, because this I'm currently working on. So I'm saying that this is my highest component, C10. So if I want to play with its critical pressure or critical temperature, I will just modify these. And I can keep playing with them until I get a match to, let's say, bubble point pressure. Okay. So this is one way that you can do the tuning. Then once again, the second function that I'm showing you over here, this is not uploaded this is not in the uploaded version. I will soon. This is simply checking if the entered mole fractions are equal to 1 or not. Okay, so at the moment, I'm not modifying critical temperature, critical pressure, just multiplying them by 1. And I check, and it's telling me that the sum of mole fractions is 1. So that is good. So this is, I think, good check to do. This function I'm not using. This is the Wilson's equation. This is Wilson equation provides you with the first guess for the K values based on critical pressure and critical temperature. Then if you're familiar with the flash theory, these two functions just based on K value only calculate the volume of the composition of liquid, composition of vapor, and the mole fraction of liquid and vapor. Okay, So this function, flash, vcalc, and this liquid vapor mole fraction. Okay, they are basically just work on the flash theory. Then this is where it starts to get serious. Now I'm starting to model the equation of state. Equation of state, the Peng-Robinson equation of state. It can be written in such a way that it provides you, calculates the fugacity of liquid and fugacity of vapor. So these are, it requires various parameters, which I call A, or in fact, they're called A's and B's. So what you notice, and this is omega AO is sometimes treated as a regression parameter, but here I'm not. Okay. So I calculate A's and B's, and then finally I use those and calculate the equation of, enter them in the equation of state, which then outputs liquid Z factor and vapor Z factor, zeta liquid and zeta vapor. Okay. So they're all part of the same game. Okay. And then this function actually then calculates the fugacity based on the calculations up until now. And this is a cubic equation solver. This is available. This is fairly publicly available. Okay, just solves cubic equation because the equation of state Peng-Robinson is cubic in nature, meaning it's like x1 plus x square plus x cube is equal to some function, like that kind of thing. So in order to solve that, I needed to write this cube root solver. One thing to be careful is that this cube root solver can provide answers in real roots or roots with iotas. So what I have done is that when I extract the answers, I'm just taking the real roots, and that means that you have a real solution. So this cube root solver, when it gives you two real roots, that means that you have a two-phase composition. And when it gives you one single root, that means you have one-phase composition. But then there are further checks that we carry out to make sure that, to find out if it's liquid or vapor, to find out if it's single phase or two phases. Now, this is the crux of the matter, okay? I'm calling it this function workflow. And this workflow is basically assimilating everything. It's to begin with, determines if it's single phase or two phases. And if it's two phases, then it determines the zeta for liquid, zeta for vapor, calculates the fugacity for liquid and fugacity for vapor. And then basically it iterates until the fugacity of each component in liquid phase and in the vapor phase are the same. That is when you would have equilibrium. So this is an iterative process. And you might see that even inside the loop, I'm checking again if it's single phase or two phases. This is because some compositions do not appear to be single phase outside the loop, but inside the loop, they become single phase. So I'm just being careful here. And then this finally outputs. So if you were to use this function on your own, simply you can use this function independently with the workflow function. It requires pressure, temperature, and composition. Okay. And based on that, it can output the composition of the liquid, composition of the vapor, mole fraction of liquid, mole fraction of vapor, and Z factor for liquid, Z factor for vapor, liquid volume, vapor volume. So this is the main, as it were, the heart of this program. And this I've tested against commercial simulators, and this is fine. Okay. Then this function is black hole. This is only to, it flashes, continuously flashes the fluid at different pressure. Okay, sorry. Is there a question? Henry, is there a question?
No, it's, I think someone talking.
Okay. I hope everybody's following me. Okay. Then this function black oil basically is designed to write out tables or let's say generate information on formation volume factor and RS against pressure. Okay. And this is pretty much it. This function, once you execute this function, it will write out lots of details which may be hard to read, but it's sometimes good. Just follow the headings, okay? And it will guide you, as it were, because it's showing you the reservoir pressure, temperature, compositions at each stage, and the liquid volume, vapor volume at each stage. Then now this molecular weight function, this density, and these functions, they are simply coding the Lorentz-Bray-Clark correlation for viscosity. Okay, so there's no magic there. And it finally uses this function, or well, it's not quite a function, but if once you run this cell, it will generate all the information for viscosities. And finally, these functions I'm using to generate, assimilate all the output from the two functions, the viscosity function and the black hole function, in the form which can be used in Eclipse and can be plotted. This, when you see PVTO under US is PVTO undersaturated and this PVTO saturated. So I'm assimilating them separately and then putting them together. Okay, this PVTG function and PVTO con function, this is for gas condensates, and this PVDG function and PVTO oil function, this is for oils. And finally, if fluid is gas, it will make all these plots, and if fluid is oil, it will make these plots. Okay. So now let's see if I can run them for you. Okay.
Hi.
Hello.
Hello. Hi.
Yeah.
May I ask my question, or I'm interrupting you?
Yeah. No.
Please go ahead.
Okay. Thank you for your presentation. That was really interesting. I just wondering, is there any trial version of this PVT Python available somewhere if I wanted to check with myself or not? I mean, later on after the. If I wanted to work with this, something that to this package that you made it.
Yeah, it's available on GitHub. I've uploaded it on GitHub. We can provide you the link. I think I provided the link on.
I'll find it. I'll put it in here, sir.
Okay. Yeah. Okay.
Mohtaba, could you please mute your line? Thank you.
Okay. Right. Now let's try and execute this guy. So I will execute one cell at a time. Okay, this is main function. Let's execute this. Okay, it's run through, and then these functions.
Mohtaba.
Yes.
Are you asking questions?
No, I'm not asking. I said I'm muted. Sorry.
You are not muted. Could you please mute your line? Thank you.
Okay, let me carry on then. Okay, I'm executing these functions. Basically, if you were to run it outside of Jupyter Notebook, you would simply say Python and the name of the program .py, and it will do everything for you. And you see, when I clicked on the gas function, it did not do anything, but now I'll click on this oil and it will generate everything for me. So let's look at the output. This is the output. Oh, by the way, these tables have also been exported in Excel format. Okay, so it will write out two files, pvto.xls and pvtg.xls. So you can review those. So this is very similar to what Eclipse requires, except that Eclipse does not want these values. It only wants saturated RS up to 1.038, and thereafter it doesn't. So I've just put in a warning over here that you might need to manually edit, and what you need to manually edit. Once again, these are very easy to fix. I've just not paid attention to it. So this is PVTO keyword, and then this is PVDG keyword. Okay, and then it's making these plots for me: formation volume factor versus pressure, solution gas oil ratio versus pressure, viscosity versus pressure, okay, viscosity of oil versus pressure, and formation volume factor of gas versus pressure, and viscosity of gas versus pressure. Okay, and this is simply giving you the liquid mole fraction versus pressure. So it's telling you basically to identify easily where the bubble point might be. So it's somewhere around 2000 psi or 2000, maybe 100 to 200. And now this once again also agrees fairly well with the commercial simulator. Commercial simulator would also tell you that the bubble point is 2200, 2300. So this you might say has been pre-run. Let's change the composition and see what happens then. Okay, so instead of, I will just activate this composition. Okay. And okay, and then oh, sorry. Okay, now this is the main function that has been run. It's giving you the compositions, etc., at each stage and the volumes at each stage. Okay, I just need to make sure that it comes out more neatly in the next version. Okay, and these are for calculation of viscosity. So now that function has been run. And then now let's run this oil function again. Okay, so now this is for a different oil. You see, it's giving me a different answer. Okay. It's giving me, and then if you look at the plots, BO and RS, and I need to, I think, restart and clear the kernels because it's writing everything twice. Okay, but don't worry about that. When you execute it, it's going to be okay. Viscosity, PG, and vapor viscosity. Okay, and then the liquid mole fraction. So once again, this works. Now let's try it for a gas condensate. Okay, so let me just comment this out. Okay, and let's activate this gas composition. Okay, and we will use the same reservoir temperature. Okay, I hope it works. I can't remember, but I need to specify that the fluid type is gas. Okay. Okay. And let's see. Okay. Once again, the sums are okay. And then let's execute the BO function. Okay, let's execute this. Okay, and then let's also execute the viscosity. And okay, so now we've run it for the gas. So now it's given you the PVTG table. And if you can see that it's giving you values at undersaturated values as well. Okay, saturated values and undersaturated values. Okay, first line is saturated, the next is the corresponding undersaturated. For sorry, this is PVTO, and then this is PV. I think I need to rerun these all the functions. I'm sorry, I think I might have just introduced a bug, but on the version that I uploaded in GitHub, it's all okay. So I don't know what's going wrong. So never mind this, but then I've just demonstrated it for 2 oils and it's working okay. So now if there are any questions. Hello? Any questions?
No, apparently not.
Huh?
No questions
Okay.
so far.
Okay. Right. So the version that is uploaded in GitHub is fine. It's working for both gases and oil. Just might have introduced some. I was just playing with a few things, so don't worry about that. Okay. Right. So shall we then end the show? Okay, if there are any questions, then I think myself or Alejandro can answer, or you can direct them directly to me or Alejandro.
Yeah, there's none for me. I thought it was actually a really good presentation, so thanks for doing that.
Mm-hmm.
A lot is going over my head, I have to be honest. But
Yeah, but
yeah, great.
So okay, can I help with whatever's gone over your head? Can I like just make sure that it goes into your head? Okay.
Oh no, it's fine. Like it's okay.
Like basically, it's, let's put it this way. This is, as it were, a cheap solution, a very cheap solution, or a free solution. Not even cheap. This is a free solution in cases when you don't have a commercial simulator available.
Yeah, and absolutely, that's the thing. So it's doing.
Yeah, so it's already been uploaded on GitHub. So just
Yeah, no, and also a bit of automation of processes. I can see it if I have, I can automate the process of generation of a PVT for simulation cases from Python. And if you use SciPy, you can optimize some of the coefficients, the input coefficients.
Mhm. Yeah,
And
I'm going to work on that in the coming versions. Yes, I'm going to work
yeah,
on that.
yeah,
Yeah, it's easier to make that step, isn't it?
yeah.
Yeah.
For instance, I think that cubic equation is good that you have it explicitly there. But if you use SciPy optimize and you use least square of fsolve, one of those optimizers in SciPy optimize, it might actually be faster to get to a solution. It might not be an issue for the type of problem that you're solving at the moment, but SciPy it's probably will give you a bit of more of optimization.
Okay. Another feature that I think I should have added to very begin with, and just overlooked it, that I want to be able to do prior to writing out BO, etc. It should also perform the differential liberation experiment and constant composition experiment, and in case of gas condensates, constant volume depletion experiment. And you should be able to compare your input data with results, and that is honestly fairly easy to do, and I'm working on that. I think that version I will put on GitHub in a couple of weeks.
Yeah, we can. I'm sorry, if you want, we can work together on that, and I can think on how to because now you have the experiments calculated by the tool, and then you have a PVT reported, so we can find the tweaks that we need on the equation of state, the input coefficients. So
yeah, okay, I think that will be, let's make it the second step to begin with. Let me just make sure that it can compare the experiments.
Exactly.
Let me work on that.
That's very good what you have produced.
Okay.
And one question I think for the benefit of everyone that is probably willing to learn Python. How many sweat and tears this cost to you?
Okay, this costed me honestly. If you want to add the time that I spent just learning Python, okay, let's exclude that. Let's only include the time that I spent just working on it. So from the beginning to, I think I started working on it in December or January. Okay. And then I had a good enough version available by summer. But then Alejandro, and I know, of course, I was discussing with Alejandro that every time I would want to release, I said, okay, no, let me make sure that this is also working right, or viscosity is coming out right. So that kind of thing, then basically, I would say, but then you must ask me how many hours I was working, say, every day or every week. So I would say that I was working on it like on an average, say 10 hours a week. Okay, 10 hours a week for, let's put it this way, 6 months.
Okay, good. Thank you, sir.
So that's quite a lot of sweat and tears.
Yeah, that's a lot of work.
Yeah, and to be honest, the first person that I shared this with was my previous boss. He was a very nice gentleman. And while I was working for him, I asked for a PVT simulator. He did not have a PVT simulator, PVTI or PVT sim license. I asked for it. He said, well, we can't afford it. We are not Saudi Aramco. So I had him in mind. So once I had completed this, I wanted him to have it and just try it out.
Awesome.
So now
yeah, that's very nice. And thanks for sharing. It's
okay.
It's really helpful for everyone, I guess.
Okay. All right. Thank you very much then. Okay.
Yeah, thanks again.
Thank you. Bye.
Thank you, Mansoor. That was awesome. Thank you very much. Thanks, everyone.
Thank you very much. Nice talk, nice presentation. Bye-bye.
Thank you. Bye-bye. Everybody, bye-bye.